Hello, everybody. Welcome to another episode of Building Better Systems. My name is Shpat Morena.
And I'm Joey Dodds.
Joey and I work at GAWA, a computer science research lab focused on trust in critical systems. Today, we get to talk with Ankush Desai. Ankush is one of the main developers behind a language called P, which is a modeling language for concurrent systems that's has been seeing some success and use in industry. He's also a senior applied scientist at Amazon Web Services. And in this interview, we get into what P is and the uses and what has made it somewhat successful. And then we also talk a little bit about bug finding in general and what it takes for formal methods researchers to build tools that are actually useful to applied engineers. So let's get into it.
Designing, manufacturing, installing, and maintaining the high-speed electronic computer, the largest and most complex computers ever built.
Thanks for joining us, Ankush.
I'm excited to be here. Thanks.
Maybe we can just jump in. I'd love to hear it. There's this modeling language for distributed systems called P that is sort of your pet project. It's something you're proud of. Can you tell us what it is?
So P is basically a programming framework. It's a high-level programming language. It's a state machine-based programming language for creating formal models and writing specifications about basically concurrent distributed systems. So basically, it's you can think of it as giving a high-level language using which developers can create formal models of their complicated systems, but as communicating state machines. So which is how basically normally developers think about their complex system design, right? As state machines that evolve from states and communicate with each other. So basically, P provides this high-level language to capture that protocol logic, and then it has several backend analysis engines to show that whatever you modeled in this language or whatever your formal design is, it satisfies the correctness specifications that you want your system to satisfy. And then basically it also has a code generation so that you can generate code and execute it. But the main thing is a high-level language with an analysis engine for creating formal designs and so on.
It sounds like it's somewhat different from other modeling languages that are out there. What makes it different aside from the sort of state machine part of it?
Yeah. I mean, actually, so at the core of it, there is no real difference, right? I mean, there are so many different formal modeling languages that allow you to capture your formal design in a high-level language and have backend analysis engines and so on. So in that aspect, P is nothing different. The main thing I think that has led to P being used by developers and in industry and in academia is because it's a programming language. So basically, it's a it's a state machine. It provides you this textual way of syntactically writing state machines, but the functions inside these state machines are basically imperative programs. So and which developers are very much familiar with writing, right? So the main thing why P worked, I think, is because it's a modeling language which feels like a programming language. So the developers are not using math or mathematical formulas when creating these models, but they are writing programs, but at a higher level of abstraction of state machines.
Got it.
I think that's the real difference.
The idea then is I'm an engineer and I'm about to build, or I've built a concurrent system with all these processes that are changing states, and this is a nice way to write that down, but eliminate a lot of the detail that I'd normally have to write to get to full implementation. And then also it lets you think about the properties of that.
Yes.
But one of the challenges also, right, is that, if thinking about properties of systems that are evolving is like a really challenging problem, right? And so there's things like linear temporal logic and complicated logics, that, modal ways of reasoning about things.
Yeah.
The model in P is quite a bit simpler, right?
Yes. I think you touched upon a very good point, is that P is a programming language. It's a high-level programming language. And when programmer is thinking about their system, P allows them to think about it at a higher language of state machines. And so basically they can use P as a thinking tool, right? Like if I remove all the complications from my system, and if I want to think about my system at a higher level as state machines, then I can use P, and that process itself of thinking about things at a higher level eliminates a lot of gaps in your thinking. And basically, and about writing specifications is that you're right that you're creating formal models as state machines. But in P, the other thing that is really nice is that even the specifications are written as state machines. Like basically the specifications are written as runtime monitors, which observe the state of the system, and then you assert global invariance on your system based on what observations these monitors are making, which is again much more easier for the developers then to write mathematical formulas with invariance and so on. So in those cases, like creating this formal models and specifications is much easier in P.
So sounds like P has had some success in industry in being maybe adopted, maybe somewhat compared to things like TLA plus. What other, like from your experience, like, part of it being a programming modeling language that feels like a programming language and people are familiar with it, I'm sure plays a role.
Yeah.
But by successful, I also mean it helps find issues maybe with the models that you're working with. In your experience, what has caused that that it being more maybe amenable to industry? I'm curious your thoughts about it.
So first of all, you mentioned about like being used more than TLA plus, but I would not put any comparison in the sense that like TLA plus has its own place, right? And P is and in fact, like TLA plus, like P takes a lot of inspiration from TLA plus. But one of the things, like I mentioned, was that TLA plus, like Leslie Lamport says, is like a way of thinking about your system mathematically. And that has its own space, because when you are reasoning about a system at a very higher level of abstraction, it's easier to think about it mathematically, right? But then as you start adding details into your system, where you're going to the low level details of your system, how low level components interact with each other and so on, now still thinking about all that mathematically is super hard. So TLA has a place where TLA and other kind of tools like Alloy and so on, which are mathematical modeling languages, have their space because they provide you guarantees, but they work at a level of abstraction. And obviously P basically what it does is it gives you a programming language for modeling. So you can model even a detailed system in it. You can capture everything that you have in your implementation in P, because the origin of P was actually as a modeling and implementation language, and so on. So, but obviously, when you add details into your model, you start to give out this, you give up on proofs and guarantees, right? Because your system itself is a model that is modeled in P is so complicated that it cannot provide you guarantees anymore. But in the reason why it worked, like your question was why it worked out in industry, is I think because having this way in which you can create detailed detailed models of your system, and then having an backend explorer that can that uses various heuristics that are there in to find concurrency bugs in your system. These two things together helped in the application of like the success of P in industry, basically. Like the ability to create detailed models and then using scalable searching techniques to find corner case concurrency bugs, basically.
When you're contrasting P with tools like TLA Plus or Alloy, it sounds like one of the differences you mentioned is that you have that high level of abstraction available to you, but you can describe quite a bit more in a straightforward way in P. And part of that sounds like it just comes from the idea of, and whether P did this on purpose or not, I guess maybe you can tell us, but the idea is like, we have all these things we want to say about concurrent systems. How would a programmer want to say them? And that's really kind of the guiding principle in the design of P. Is that accurate?
Yeah. I mean, you would like to have the ability to capture implementation level details in your formal modeling as well. If you want to, if that implementation level detail is important to the correctness of the system. So yeah, and basically, like you said, Ed, P makes it a bit easier to capture those details as compared to other languages.
And was this kind of an intentional design decision?
Yeah.
Like someone was like, well, there's this shortcoming, or how did this kind of come to be in P? How did this what made it clear that this was an ideal way to do things?
I think yeah, you're right. I think the main reason for this was we were when we started on it, I think we wanted P to be not just a modeling language, but also be an implementation language. So the idea was to use P as your describing your design and so on, but also keep evolving the P models to reach to an implementation, and then do code generation to basically deploy the generated code and so on. So we were never thinking of P as just as a modeling language, but both as a modeling and an implementation language. So now, if you want this to be an implementation language, you have to allow the ability to capture this low level details as well.
That makes sense. And you mentioned scalable backend analyses. So you give up on something, but presumably that's still okay. How does that all work out?
So even there, it's interesting. What I meant by scalable backend was that we have multiple backends for P. We just don't have one. So the backends we use different backends based on what the goal is, right? So if your goal is basically bug finding, like you want to find in concurrency bugs in your design, and we want to find them. So in those cases we have this. There is this a lot of work that has been done in doing systematic concurrency testing, where you use different bounding techniques. You use various search prioritization techniques to prioritize your exploration of search and so on. And these techniques are very efficient in finding concurrency bugs in your system. So P has a backend that is a variant of basically an explicit state model checker that explicitly enumerates different behaviors. And in some cases, after a certain depth, does prioritized sampling of the search space based on different things. And this is way more efficient in finding concurrency bugs as compared to any other technique like symbolic execution or any of those things. But obviously, when you are doing this kind of explicit state thing, you don't get guarantees, right? Because you're not going to finish exploring all the state space. So when the goal is to find as many bugs as possible, we use this backend. Now, if your goal is to get some soundness guarantees, then we have an symbolic execution engine backend that gives you the guarantee that all the states for a finite program, we will explore all the states of your system. But yes, but then symbolic execution has its own scalability problem. So if you throw a way more detailed model to the symbolic execution engine, it's not going to finish. So and then we are currently working with Sanjit Seshia and others at Berkeley to build a deductive verification engine for P, where the idea would be to do proofs. But then again, like I said, if the idea was to do proofs, we can having to do proofs for detailed P programs would be hard. So now it would be like people will use the P verifier for creating very high program programs at a very high level of abstraction. So basically, yeah. So what I meant by scalable is scalable based on the goal. So if the goal is bug finding, we have a scalable engine that runs on a distributed cluster. If the goal is symbolic execution, and then we have something where it's not as efficient as fuzzing or test or explicit state model checking for finding bugs, and so on. Yeah.
In practice, what you're seeing in industry, is there a most common degree of complexity and scalability that's needed, that sort of indicating the tool should focus in a specific
So
direction
I
for
think
industrial
there as
use?
well, I mean, and my thought has evolved. Like I used to think a lot different when I was in grad school. I'm thinking, then I thought very differently, and now I think it's very different. And I can tell you an example of why I do that. But to answer your question, I feel all the three of them have their own place. I don't think any one of them is enough to solve the problem. And I really strongly believe on a portfolio backend, like in the sense that if let's say there is a principal engineer or a senior principal engineer in a team who is very first time trying to design a distributed protocol at an abstract level. Let's say he's trying to come up with a variant of Paxos or something like that, and he wants to show that my variant is correct. And there he wants to convince the entire group that like he or she that entire group that basically my protocol is correct. So he would like to give a deductive proof, right? So then the proof he can use the same language which everybody else understands and then show a deductive proof, right? So that there's value of this backend. Then there's another developer who say, hey, let me add details into your protocol, but I would like to show that for finite instances of this, it works correctly. So maybe they will use the symbolic execution engine. And now they are adding more and more implementation details into the Paxos variants, and it reaches a point where it's more than 150K line, like 1,500 lines of code. Then I think doing a proof for it is super hard. Symbolic execution engine, we don't know currently, it doesn't scale. So then there is a place for the third backend. So I really feel that based on the crowd, the developer community that is doing that work, all the three of them have its own place. Yeah.
Is it possible to have the models exist together? Like, can you do sort of a refinement kind of thing where you have your high level model coexisting with your low level model, and you're able to show all that stuff at the same time if you kind of commit to this approach over time?
Yeah. And I think so. This has not been done, and I don't know how to do it right now. But I really think that it would be, like you said, it would be really great if we had a single front end with the capability to use any methodology that you would like to analyze that program. Like you have a front end with the same like it need not be P, it can be any other language, which allows you to write inductive invariants and do a proof for it. Then it allows you to do a refinement to a more detailed model, and there maybe you're not doing proofs, but you're doing something else there. Then you again go down, and eventually you reach to implementation. But when it becomes so detailed, but it's still in the same framework, it's still in the same programming framework, and there is connection between each layers. And maybe the connection between each layer, in maybe the very top layers, it's still done using proof. But in the bottom layers, now it's so detailed that you don't do proof, but you do testing. Yeah, but I think that could be a very nice thing. Yeah.
So for all the concurrent systems researchers out there, just so hard up for topics to study, there you go. You can try to build this unified system.
Yeah.
I don't know. I want to just like pause for a minute, because I think so. We live in the world, I guess, often of sequential verification, and we're talking about here about concurrent verification. For people that haven't spent a lot of time in that world, can you explain just why it's so hard to reason about these systems?
Yeah, I mean, so at least the way I basically explain to people is that in a sequential program, the only form of non-determinism is input, right? Like you have to make sure that given a sequential function, given some non-deterministic inputs, you want to make sure that after the function is executed, the outputs are as expected, right? So the only non-determinism is different types of inputs that you can receive. Whereas in a concurrent system, you still have the input non-determinism, because your system gets values, and you have to make sure that your system is correct in the presence of input non-determinism. But in addition to that, you also have to make sure that it is correct with respect to the control non-determinism in the sense of concurrency. Like and these functions, they can execute in parallel, so they can mutate states in parallel and so on. So not just the input non-determinism, you have to make sure that the system is correct even in the presence of concurrency or control non-determinism in your program. And that's why it's super hard. So your invariants that you write to prove these programs, in the original sequential program, the invariants were on inputs, and then saying that the precondition on the input and the post. Here, your invariants also have to capture the basically the interleavings of messages that can happen in the system and so on. And that's where it's or the interleavings of functions that can happen in the system. So that's where thinking about one of the most hardest part when doing this proofs for system is you now have to think about, when I'm reasoning about the correctness of a program, I also have to reason about what the state of the other program would be when I'm doing this, and sorry, process would be when I'm proving this process correct. And that's where the hard part is in doing verification for concurrent programs. Yeah.
I have a friend that's spending all their time doing like sort of a manual proofs about concurrent programs. And I call them sometimes, and they say like, "Oh, you're just doing sequential verification, huh?" I'm like, "Yeah, it's still hard."
Yeah.
I promise it's hard.
So actually, I would say one more thing here is that there is a lot of work in academia on converting parallel programs into sequential representations and then doing proofs. Like, and there is this idea of sequentialization of concurrent programs. Basically, if you can think about a concurrent program as a sequential program with a scheduler, where basically what you do is at each step, after you take a step of a thread, you convert your whole concurrent program into a sequential program where after each step, you reach a conditional inside the scheduler, which says, hey, which next, not where you non-deterministically choose which next process or thread to execute, and which can be any, like it's a if have a if choice or something like that, right? You non-deterministically pick any thread, and then you take that thread, make a step again, and that's in a loop. So it's a sequential program where at each conditional you're picking which next thread to go, and then you prove this sequential program correct. And there has been a lot of work on basically doing sequentialization of concurrent programs and then applying the same techniques that you use to prove sequential program correct. Now you can apply it to prove concurrent programs correct. But again, the complexity becomes more because now you have you have represented a non-determinism corresponding to concurrency as basically control non-determinism in your loop, right? Like you have this conditional, and so now your invariants become more harder.
Yeah, I can imagine pointing an engineer at this and saying like, yeah, you have how many nested if statements with symbolic cases there? The tool would it'd try, but it wouldn't have much luck.
Yes.
Would you suggest, let's say there are listeners who are working on developing really a concurrent system, maybe with more, let's call them traditional sort of methods. At which point should they reach for P if they haven't at the beginning?
I would say at the start. I would say when you are starting to think about your system, that's when you should start with P. Because what we have found, even when we were using it in the past, like with Microsoft or even right now in AWS, what we have found is that basically P has its own value. Like it's not the P checker that finds most of the bugs. It's actually the process of creating formal models and writing specifications for the system itself that would find you like maybe a large factor of the bugs that are there in your system, and it's basically basically I call it as P being used as a thinking tool, because whenever you say, hey, to a particular engineer that go create a P model, the first thing that he or she would have to they would have to do is basically go and think about at what level of abstraction do I want to create these models, right? And what are the components with which my system that I am trying to model is interacting with? How is it interacting? What are the assumptions I am making about those other components and so on? So even the process, so even before they write a single line of P code, they are thinking about all this. And then once they start writing it, that process of writing and capturing this thing itself finds a lot of bugs. And this is nothing to do with P as such. Like any language they would have used, this is the process itself eliminates a lot of problems. So it's always better to start with P early on to remove all these bugs, and then you can, as your system evolves, you can keep modifying the P models and specifications and so on.
Makes a lot of sense.
Yeah, I have a. I guess I'm going to pitch my own thing here. I have an article, a one-page article called "You Already Know Formal Methods," and it says almost exactly that. It's like, I don't care how you write it down. Like, just sit down and try to say what your system's doing, and you're going to realize that like you weren't thinking through it quite as well as you could have if like you write it on paper. But then I think, if you can manage adding a degree of rigor and like structure, like what P provides, will really help. Like, helps you just, the less you can get away with sloppy thinking, the better you're likely to do in this kind of process. And so, having a language with a little, a bit of a type checker and a bit of structure will help even more in that process. And it's always amazing that you don't even really have, like, running the tool will find some of that really hard to find stuff, but you'll shake out so much of the easy stuff right off the bat. That's, I think, always surprising to people.
Yeah, in fact, I when I was in grad school, I read several of these articles which said that, hey, writing specifications is super important. Writing specifications is super important. And most of the research that I did was on scaling P, like trying to make these analysis scale better. And so my focus was, how can I use the checker to find as many bugs as possible, right? And then when I came to industry and people started using P, it kind of was like a deja vu thing that, hey, whatever people and the great researchers in the community were saying about the importance of writing specification, it's actually true. So, so it was like, okay, great. I think, So I now understand why formal methods community really emphasizes on writing specifications, because just writing itself is good enough.
Actually,
it's a step. It's not good enough, but it's a step towards getting there. Yes.
Yeah, that reminds me of a question that I didn't get to ask earlier, which is, I mean, P has some history now, right? I mean, at least 10 years or maybe almost 10 years. How did you get started with it, and how did it get started? Basically, what was your journey with it?
Yeah.
Yours personally.
So I mean, I share this thing with most of the people who say, hey, why did you come up with P? Like, what is and I very proudly say this, and I feel like, and I very strongly believe that is the reason why it works out, or maybe it is that P was not designed by researchers. It was not designed by formal method researchers. It was designed by USB device driver developers. So the thing is, when before starting grad school, I was part of Microsoft Research, working with Sriram Rajamani, Shaz Kadir, and so on. And at that time, the USB 3. The device driver team in Microsoft, they wanted to go from USB 2.0 to USB 3.0 and basically build a completely new set of device driver implementation for it, which was completely concurrent. So USB 2.0 did not have as much concurrency, and they wanted to exploit concurrency for performance. But they were scared that when they are coming up with this concurrent design, they do not introduce concurrency bugs into it, which may lead to blue screen errors and so on, right? And so what they did was basically they wanted to use a concurrency analysis. So at that point, Sriram and Shaz had built this model checker called Zing, which was an explicit state model checker for concurrent system. So what the USB device driver team did was, when they were trying to create the design for their device drivers, they used Visio diagrams. So Visio is this state machine diagram, or basically diagram tool from Microsoft, right? So they created these state machines in Visio, which basically is what P state machines are right now. They created these state machines which described the whole USB protocol stack, and they wrote like PowerShell script to go from those state machines to Zing language, which was a model checker, to analyze their design representation and find bugs in them. And that process found a lot of bugs, like more than 100 bugs in their design itself. So the whole idea of having state machines, concurrently executing state machines, so the language of it was basically designed by the USB device driver team. The whole idea of thinking about things as state machine was their idea. What I think Shaz and I and Shira, what we did was we gave it a formal semantics. Basically, what they were doing, we gave it a language semantics and wrote a compiler for it. And they basically took it from there. But I think the whole idea of having a state machine as a language for writing things and then having a backend analyzer was basically driven by the developers. And they came up with this whole idea.
That's fascinating to me, especially since it is finding use, and it's actually, I'm gonna maybe ask a question, see whether anything generalizes for the let's say there's formal methods researchers or just people working on the next generation of tools and whatever their research is about. When you think about people doing that with a tool, whether it be a modeling language or anything else, what can they learn from this aside from just knocking on doors at big companies and saying, are you working on anything that we can take and formalize a little bit more? I'm curious whether you thought about that at all.
Yeah, I mean, so Shaz and I had a lot of conversation about this. That hey, what is the real thing behind this? It's definitely not the language. It's definitely not. The P is not magical. The P language is very much similar to state charts, which has been around for a while, right? Like the idea of writing your protocol as a state machine is not our idea. Like it is very well known. So what is it that is working here, right? What is it that we should give to the developers that will help them in building and reasoning about their system? And it came down to three very basic ideas, which are again derived from existing ideas in our community. The three basic idea was we need to give a language. It could be any language, a language that allows developers to write their system at a higher level of abstraction. It could be state machines, it could be actors, it could be communicating processes, whatever is suited for that team. There has to be this high level language. Okay. Once you have that language, which is good enough for creating formal models and writing specifications, what you need is a very simple mechanism of controlling non-determinism in that language so that you can explore different behaviors in that system. Okay. And now when I say controlling non-determinism, you can control non-determinism either using fuzzing. You can control non-determinism either doing symbolic execution, exploration, and so on. But what I meant was based on the flavor you want, you can just introduce a controller that allows you to do more than what would happen if you did testing in production, right? Like you need a way in which you can control non-determinism, explore different things, and so on. So that's the second thing. So the second is control. But even when you have control, the third thing is if you hit a bug, you need to have an ability to reproduce that bug. Okay, that's it. So those were the three basic things that we found was super important. If you build any framework, it could be analysis of real implementation and anything. If you could do these three things, where you have the control over what you explore in your system so that you can systematically explore different things and you can explore things which have low probability of occurring in a production system, right? So you can build a controller that explores behaviors in your system which are low probability of occurring in a production system, but the ability that whenever there is a failure or assertion violation, you can reproduce it. And that's what model checking basically allows you to do, right? Like you produce counter examples which are reproducible. So those are the three basic things. If you provide that in any framework, it would work with the developers. And I think that answers that the key thing, if you do testing, you can see things failing, but debugging those failures for a concurrent system is super hard because of the inability to do reproducible bugs, right? I mean, you can run the concurrent program again and again. In some cases, it fails. In some, it doesn't. Yeah. So I think those are the three key things. Yes, I think.
I think I'm gonna disagree with you a little bit. That I think the language does matter, right? I think we started off with this, or we had this idea a minute ago that was like you should write specifications, right? Like that's a good thing. Do that, you're going to be better off than you were before. So like the very first question we should ask is like, how do we help people write specifications? Like if you give them a crazy language that looks something like they've never seen before, then they're less likely to write specifications than if you give them something that looks like what they've worked on every day, right?
Yeah.
And then the next question is like, how do I make use of this thing? And if you say like, well, like learn this interactive prover and learn, learn temporal logic and then write these specifications and like, just, you're smart, you can do it. They'll be like, well, I probably could, but like, I got some other stuff to do. And if you're like, well, push the button and you can try to fuzz it today and it'll find some bugs for you. And they're like, all right, I can push a button. And they're like, but then they ask the question, right? They're like, all right, well, I pushed the button and that found some stuff, but can I do more? And then all of a sudden you've got people and they're coming like, all right, well, how do I like take this a little farther? And then you're like, then you got them on the hook and you're like, next year they're hacking in concurrent proofs in Coq with temporal logic and they don't even know what happened. But those first steps are super critical, right? And it sounds like, the sort of way P came to be was like engineers wrote what they really, this is how I think about writing down a system. And you modified that into something that other engineers could use in the same way. So I think that matters quite a bit, but
and that is also like from what you said, right? I feel like if you have this single framework that programmers like, and it allows you to do fuzzing and proof both, it then opens up a very nice area which people have been doing in isolation, right? Where you can use fuzzing to learn invariants to do proofs, right? Like, but if you don't have a single unified framework, how are you going to combine these two ideas in a practical way? I think that is the other motivation I feel that it would be great to have everything in a single framework. Yeah.
We brought this up over and over again in this podcast, but if you're working on a tool like this, find a way to work with people who maybe are, working on applied stuff, maybe not with that level of assurance. Bring them in somehow and see what happens. You might hate what you see, but it's going to make for a better tool.
Yeah, and I think there also it's very important to kind of not go to engineers with your tool, but go and ask them what your problem is, and then see if your tool is the right fit or what modified version of this tool would be a right fit.
Listen to people and see where they're coming from.
Yeah.
Wow,
I think
makes a lot of sense.
So I mean, there's very interesting thing is that like for example, not everybody needs to use formal methods, right? It has its own place. Like, I mean, not like, for example, not every part of the software needs to be verified to be correct.
Yeah, well, if software is correct, it's correct whether you verified it to be correct or not, I guess is one argument.
Yeah, just write correct software.
Yeah, no,
yes.
Everybody's doing cost benefit all the time, right? And if the cost of a bug is super low, then why would I pay a huge cost to eliminate that bug, right? And it's it's insane. Like you've got to prioritize, right? We all have a million things we want to do, and we all want our software to be correct. And at the end of the day, sometimes we have to make choices that we know result in possibly slightly less correct software.
Yes, and I think that is what is very evident in an industrial setup, which I found very interesting. Is and even when and not just industrial setup, I think, for example, when I was in doing my undergrad and masters, I worked on this project where we were trying to build nano satellite, and we never used formal verification there, and basically like the thing was that we initially did a lot of reasoning about systems and try to make sure that our system's correct. But soon basically the head of our project came in and said that, hey, we have to do, when we started this project to build this student satellite, we were given a budget of 2 crore rupees. We have eaten up a lot of this money. We need to figure out a way in which we can deliver this in time. So what is the best way that we can deliver this in time, but with having some assurance about that it would work. So you cannot spend all your energy on making the system correct. I mean, obviously, if it's security and privacy, like things like that, which are super critical, you have to do something mathematically correct, but not for the whole system. So it would be nice if in some ways we can not just. I think the next thing would be interesting is how can we use formal methods to increase the velocity of the developers to deliver them their services. Not like always prove them to be correct, but for critical components, you have to prove them correct. But then also for the things where you have time budgets, how can you increase the velocity of the developer to deliver those in time? Yeah, and that could be interesting.
Yeah, and I think that's where a lot of that idea of let's make it easy, let's make it part of your sort of day-to-day workflow to do system modeling. And even if you never get to the proofs, it's like you're in better shape than you were, and you've left something for the next engineer as well. Like because maintenance is a problem for everybody, right? And like that's the place where sometimes those short deliveries, like you really like take on that tech debt in a way that's it might have been unacceptable, right? Like you might have just made a mistake there. Whereas like just that little bit of modeling can leave something for the next person to get that toehold and kind of understand what's going on in the future. So I think, that's like, I mean, the trick I play is for everybody needs formal methods, but like what you're thinking of formal methods, like it's everything, right? Like you write that thing down on the paper, that was formal methods. You like formal methods, it's I don't make the rules. So that's the other way to take it is like, this is all formal methods, right? Like just be a little formal, like try to say what you meant to do. And that's a step. But we definitely scare, like, I write articles about like, hey, we did this amazing proof with AWS or with this blockchain company and it was huge and it took engineers full time, for half a year, and it's amazing, and it's the most rigorous thing anybody's ever done, and I love that stuff. But like that's there's no question that most people shouldn't be doing that with their time.
Yeah, I want to ask an adjacent question and put P aside for 1 second. Well, maybe not. I mean, frankly, it's part of it, but I know that you have very strong opinions about the following. In terms of bug finding, there are some techniques that work maybe unreasonably better than other techniques. Specifically, I'm thinking about random fuzzing. I'm hoping you could talk a little bit about that.
Yeah. I think this is also from experience. I think this is from how. So, for example, when we started working on P, the backend engine that P had was Zing Model Checker, and it was trying to do explicit enumeration and be exhaustive and show that given a finite program, it is correct, right? So we were always, the goal was to do proof for small systems. Then there was a time when Shaz and a lot of other people came up with this bounding techniques called context bounding, delay bounding, and so on, where because the problem of doing complete exploration of a program was becoming hard, why don't we do bounded exploration? But then while doing bounded exploration, like say that we explored programs till this bound, then we have increased the bound, and then say we explored this, so that we can give some bounded exploration guarantees to the developers, like saying that, hey, I have explored, for example, in context bounding, when you say that I have explored everything till a context bound of 2, it means that if there is a bug that can manifest with 2 context switches in your program, then if I say that I could not find any bug with context bound of 2, then there is an absence of a bug in your system that can be manifested with just 2 context switches. There can be a bug with 3 context switches, but there would not be, and so on. So they came up with these ideas, and this was great. But soon, these techniques were being projected as not being bounded verification techniques, but as bug finding techniques, in the sense that if you use context bounding, you can find bugs faster than tools that are doing exhaustive search, right? But then that's not the right way of thinking about it, right? Like, because the goal now, your goalpost has shifted. Your goalpost initially was to do proofs, and then you have full proof, you have bounded proof. Now the goalpost is not proof, it's bug finding. So then if your goalposts have shifted, the baseline should also have been shifted, right? Now the baseline should have been what other techniques can find bugs faster than context bounding. So there were a series of paper, and I think I also wrote a couple of, like, one of them on how delay bounding is better in finding bugs, like faster in finding bugs than traditional depth first search exploration based techniques, and it beats context bounding and so on. But I think the problem was we were not thinking right. And there were a lot of papers like this. Then Alistair Donaldson and his group in Imperial, they wrote a paper where they took all the old benchmarks for context bounding, delay bounding, and so on, and they just ran random fuzzing on these benchmarks and showed that the same bugs can be found with random search. I mean, obviously, in some cases, context bounding found it faster than random search, but then difference was very small, right? So, and then in some cases, random search was able to find bugs faster than context bounding and others. So the thing is, this was like a big alarm for, at least for me, not alarm, but like this was a good realization for Shaz and myself and others that, hey, we are not thinking, the baseline should have always been random search, right? So now I feel like if you are trying to say that this technique finds bugs faster than any other, how about, does it really do that as in comparison to running a fuzzer on a distributed cluster? Because the fuzzing is the simplest idea, right? I don't have to give any bounds. I don't have to think about anything. If it cannot beat fuzzing, then just don't introduce it as a new idea, right? I think that's what my feeling is.
When you're doing paper reviews or like program committees of conferences, you're gonna return papers and be like, please compare this to random fuzzing, and then resubmit it.
I feel bad when I still see papers which say that we are bug finding tools, but their baseline is not fuzzing that. So yeah,
makes a lot of sense.
But what I'm saying is that I think it was just that the baseline was not correct for those papers, but those ideas are still relevant when you are looking at those ideas in the right way. Like if you look at bounded context bounding as a bounded proof technique, it's a super cool idea. Right.
Yeah. So the point is, like, you might be able to bound something and actually say something meaningful. Like maybe your program is guaranteed to have only a certain number of context switches, for example, and it's bounding that is great. Definitely do that. And you will get exhaustive guarantees, but exhaustive guarantees about a limited sort of slice of what the program can do, and fuzzing will give you no such guarantees. I think many of us have submitted a paper that's like calls bounded proof, and there's a set of reviewers that'll just be like, that's not proof. If it's bounded, it's not proof.
Exactly.
Those are fun. Cool.
Yes.
I think we've had a nice interview here. Is there anything else you'd like to talk about before we wrap up?
No. I mean, I'm super thankful. It is great. We had a nice conversation. I'm happy that I got a chance to talk to you all.
All right. Then thank you for joining us. It's been a wonderful conversation.
It's really nice to chat with you, Ankush. Thanks for joining us.
Yeah, thank you.
This has been another episode of Building Better Systems. Thanks for joining us.